Hello everyone. Today I'm going to leave my little table and go around the corner here to my workshop. So welcome to my little basement workshop. There's a saw. Here's a cutoff saw. My bench. Some cutter grinders back here. Of course, everyone needs a layout table. Here's my little granite layout table. Some tooling. And around on this side here is the old lathe. This was Grandpa's. It's probably somewhere around 70 years old. And then, of course, the little bench milling machine. And the mill is where we're going today to take a look at something. Today we're going to try to test the horsepower and efficiency of this window motor using what's known as a Prony brake. Okay, and I'll explain this, but first let's take a look at something here. Here's an old machinery handbook. God bless you, Grandpa. And you can see this is old publication. I'm going to go to the back here, or somewhere in the middle, and there's a chapter on the Prony brake. Now if you look this up, you're going to find a device that looks like this. And this was real popular back in the days of the steam engines and old-fashioned Stirlings and so on. And they had a lever length and a friction wheel and a weight and formulas, and that was popular back then. But today we find something a little bit new. I found this on the YouTube, and it was a video published by Peter Lindemann, and he uses two scales, and of course here's a friction wheel. And that's a little bit different than the old-fashioned Prony brake, but this, you know, kind of works out the same and makes the same test. Okay, so I'm sure you're asking, what do I need to have to do one of these Prony brake tests? Well, you need a couple scales. These scales came from the internet on eBay. Believe it or not, they were only about $10 a piece or less with free shipping. You need a motor, naturally, wise guy, and you need a pulley or a wheel on the motor. I happen to make this one, and I made it so that it represents a 6-inch circumference perfectly. So this is 1.910 basically diameter. But you can use a pulley or anything else that you're able to measure the diameter on, because that'll work out in the formula. Of course, the motor is driven with this pulse circuit here, and I am having some trouble with it. I think I fatigued the transistors, so I know that this test is not going to be that good, but anyhow, we're going to go ahead with it. And then you need to be able to do the math to figure out what your horsepower is and your efficiency. So I have all the formulas here as they have been represented by other people, like Peter Lindemann and my good friend Brad, the Tin Man. And I've had some nice, wonderful help from John Stone in Germany. So between all that help and interpretation, I think I finally have this right. So I made this spreadsheet that all you have to do is input the 5 variables that you need into the pink boxes, and then the formulas work automatically. So all we need to do is make a test and get some numbers and give that a try. So okay, you know what I'm going to do before I run these tests is show you some clips that I made of this motor with a kind of a test that most people would perform before they'd ever dream of making a setup like this. So I'm going to show you some of these with a with a fan going on it and installing the motor by hand and everything. Then we'll come back and we'll do these tests and see what happens. So here comes the videos then. Come on. Come on up here. Come on. Good boy. So I'm going to go over here to the power supply, and I'm going to set at 20 volts. Pretty close, and I've got the current limiting all the way up, which will give me 3 amps. And we'll get going over here. Okay, so you can see we're running pretty good here. This is some sort of a radiator fan or heater fan or something like that. My voltage picked up about 1, even though the supply is set at 20. There's probably a little bit of radiant coming back. And let's look at the current running at let's say 1.3 amps. So 1.3 amps at 20 volts is like what, 26 watts? So that's not too bad. So that's running pretty strong. Now I don't advise anybody to do this, but I'm going to do this to show you. And I'm pressing pretty hard on there. And that's a big diameter, and it actually hurts. So I'm going to kick it up a notch. So we're running at 20, 21 volts. I've got a switch here that is going to take my diode bridge and put that back across the motor. And listen to the RPMs when I do this. Alright. Anyhow, let's look at the power on this again. I'm pushing on it pretty good. And if I was to try to stop this by the spinner or the shaft, it just ain't going to happen. I'm squeezing it pretty good here. And you can see that I've actually worn the aluminum off on my fingers here. So there is some power there. Let's look at the running at 1.56 volts at this higher 1.56 volts at this higher running speed. So I'm going to push on this, and we'll look at what the maximum amperage is going to be. Hear the motor slowing down. Ouch. And about 2 amps. So at almost dead stall, it's only 40. We're only drawing 40 watts, and it is giving a little bit of power off. Let's look at another thing. This is the feedback off the diodes over here that's coming off and going onto this power rail. So I can take a couple bulbs and light them up. Let's see what happens when we light them up. I'm at 1.49 amps. I light them up, and now I'm at 1.43 amps. So is that useful? I don't know. Well, could be. It's not what the video is about. It's still at 23 volts, which is higher than what the power supply is. There's still plenty of power here that could be running a generator head, for instance, or something else, as you see in some of the other experiments, especially the asymmetric winding experiments. Plug the power supply in, and you know, these motors are sort of triggered, so they don't start right off running and jumping into place like a permanent magnet motor. Anyhow, it's running up pretty good right now. So, what about that? It's going pretty good. I already know that it's going near 800 RPMs. And let's go over to the power supply. And you can see I'm running at 22 volts. And it's running this big fan here, and it's only using 660 milliamps. Okay, I'm going to plug this battery in series with the power supply. Growing, growing, growing. I have the mic on the camera around backwards, so it's probably protecting the mic a little bit from the wind. At least I hope so. We'll see. So anyhow, there you're running at about I have 22 volts, and I know this battery is probably running about 11.5, so you know, 30 a couple volts, something like that. At 1 amp swinging something like that, it's a far cry better than a lot of the small permanent magnet motors that everybody's dealing with right now and playing with. So they're easy to make if you feel like making one. That's all you do. Wrap some wire around a rotor with some magnets and look up the Bedini Cole sequential bipolar window motor circuit, and you'll find the circuit for this little driver. Okay, so now that I've shown everybody how to test the motor the wrong way, let's go back to the Prony brake and look at this a little further. You don't need a milling machine to test this, obviously. All you need to be able to do is clamp your motor down to the table or something else like that. And you don't need to do this. You can just pull both scales by your hand. You just need to have some help or be clever about getting your readings. So the one thing about this milling machine now, this is set up so that when I pull this lever back, the headstock goes, or the spindle goes all the way up to the top, and it can't go any further. So the way I adjust the pressure on the wheel after that is down here is my crank for moving the head stock up and down on the machine. So what I do is move this up to the top where it wants to go anyhow, because there's a spring. I can lock this if I want to lock it and take my readings, which makes it convenient. And what I do is I just crank the head up until I get the pressure that I want on the wheel. Take my readings and then go over to the software. So let's take a look at that. First of all, the power supply is set at 20 volts. That'll stay at 20 volts because it's regulated, so I can just switch over to amps now and use that to get my amp reading. I also put a 12 volt battery, motorcycle battery, down here in series with it, and that's going to give me about another 12 volts. So let's hook it up, get running, and if I can, I'll check that voltage again when we're running. So that's on. Hold on, let me plug in. Okay, so now we're running, and I'm starting off here with a 190 milliamp reading, which is not one of the readings we're going to use. Everything is hooked up. I'm going to make sure the scales are on and zeroed. And we're ready to go. So I'm going to pull up to the preset stop that I have. And here we go. We're underway. I'm only pulling 11 ounces. I'm going to go up a little higher. Okay, so there's 14.1 on that scale. 3.1 on the other. I'm going to write that down right away because those scales will turn off. 14.1 and 3.1. We need the RPM. Well, we're going that way. So the RPM is, get the red dot on the thing, John. 1,405 RPM. And need the amp draw. The amp draw is 0.61 amps. I like the sounds of that. 0.61 amps. And we already know the voltage, but I'm going to give the voltage a test anyhow. Hold on. Alright, since I just shorted out the battery and blew the fuse down here, I guess you're going to have to take my word for it that the voltage was 31.9. Okay, so we're back to the spreadsheet again, and you can see it's all empty, all zeroed out. So we need to start with the top here and put the inputs in. So the input voltage goes here, and that was 31.9, and the amperage was 0.61, and that's all we need there. We go, well, let's explain something first of all. Once that is entered, the wattage will show up here. You need the wattage of the input, which is 19.459 watts. Okay, so you need the electrical horsepower before we go on below. So you need to divide the 19.459 watts by 1 electrical horsepower, which is 745.7 basically, and that gives you 0.0261 electrical horsepower. So let's go put the rest in here. We need to have the higher scale reading, which was 14.1, and the lower reading was 3.1. And we need the RPM, which is very important, and that was 1,405. Okay, that should be it. We've got all our stuff going on here right now with the formulas, but before we look at the end result, let's take a look at how this is happening. Okay, so first of all, you need to subtract the lower reading from the higher reading, and that's the pull in ounces here. So down here you see that 14 minus 3.1 equals 11 ounces. Let me move up a little bit more here. 11 ounces. So you need the total pounds of pull. So convert the ounces to pounds by dividing the ounces by 16. So here's our 11 ounces, and divided by 16 gives you 0.685 pounds of pull. Next step, before going on, you need to have the circumference of your wheel, and I made a calculator for that, which will take my my diameter, whatever I put in here, and it will convert it for me. So over here I'm going to put 1.91, which is the diameter that I machine my wheel to. And okay, so that happens to give me a 6-inch circumference. 1.911 diameter times pi equals 6 inches. Okay, next you need the feet per second at which your wheel is traveling. So first we need to multiply the wheel circumference by the RPM to get inches per minute. So we take the wheel circumference times the RPMs and come up with 8,431 inches per minute. Still not finished. Then divide the inches per minute by 60 to get inches per second. Okay? So inches per second equal 8,431 divided by 60, and that gives us 140.5 inches per second. Still not finished. Lastly, we'll need to divide the inches per second by 12 to get feet per second. So feet per second equals 140.5 divided by 12, or 11.71 feet per second. Okay, move up here a little bit. Okay, you're ahead of me, can already see the results, but let me finish explaining. So we have the 11.71 feet per second. Okay, finally we need to get our total output in foot-pounds per second. So we need to multiply our feet per second times our pounds of pull force, or foot-pounds per second, where it was 11.709 times 0.688. So now we have 8.05 foot-pounds per second. We will need the output horsepower, so we need to divide the output foot-pounds per second by 550, which is 1 mechanical horsepower. So the total output of horsepower equals 8.050 divided by 550. So that equals 0.015 total output horsepower. Okay, to get the efficiency of your motor, you simply divide the output horsepower by the input horsepower times 100 to get percentage. So the total motor efficiency equals 0.015 divided by the input horsepower, electrical horsepower of 0.0261 equals 56.11% efficiency of your motor. Okay, so this was multiplied by 100, but I don't show it in the formula. Okay, so that's surprisingly low. I think that, if I was going to make up some excuses, it would be that the motor certainly doesn't like running with all the steel around. I know I was having some trouble with the circuit. But nevertheless, I'll check the transistors and maybe set up again and try it. But it really seems funny to me that a motor that can run at less than 50 microamps and less than 2 volts and run for weeks on a capacitor isn't more efficient. But who knows? We may find out that window motors aren't real particularly adaptable to this test, because the triggering is dependent on the speed of the rotor. So when you slow it down, things could go out of tune. I don't know, maybe it was a bad idea to try this. Okay, listen, I want to make one more quick test. There's a reason probably that this window motor isn't testing very good. When I'm running at higher amperage, my driver transistors up here and the resistors are getting really hot, so the amperage that I'm drawing is across the, the components there, and I'm not really getting a true motor reading. It's all losses in the circuit. So what I'm doing is I'm running just from the power supply, running at a lower voltage, about 14 volts, and as you can see, I'm running at about 80 milliamps to start. This will give me a pretty poor draw on the pole pounds, but I want to test it anyhow, so I'm going to turn the scales on. Okay, let's see what we get this time. Pull up. I'm at 14 volts. Well, 300 milliamps, a little higher than I was hoping for. 0 on this scale. 4.9 on this one. 4.90, 14 volts, 300 milliamps, and I just need the RPMs. $11,049. 1149. Okay, let's see if we get anything different with that test. It's a little more along the lines where I run this motor in tests, so I'm hoping that might turn out a little bit better. Current one up to 330. We'll see if that makes a difference too. Okay, so I'm not going to bore you with putting all these dimensions in and everything. I just entered them already. So up here you can see there's the 14 volts. We got a pencil here. 14 volts is up here. The 330 milliamps. 4.9 ounces on the high scale, 0 on the low, and 1149 RPMs. And as you can see, that gives us a little bit better efficiency. So I'm convinced that I was burning up those driver transistors. For some reason, when I did the other tests with the fan on the motor, incidentally, here's one of the fans. I had no heat really. The power transistors were just barely warm. So something went badly wrong in the circuit here. And I'll figure it out. Maybe I'll make another test somewhere down the line. But for now, that's it. I've spent enough time on this. I hope it was some help to somebody. I mentioned quite a while back when I was still accepted on the UFO channel or forum that this would be a good kind of a spreadsheet to make for tests, and anybody who can do Excel should be able to make this kind of a sheet or something similar, and it really helps out with the tests. So okay, so anyhow, I wish everybody a lot of luck, and thank you again, Peter Lindemann, John Stone, Brad, the Tin Man. I appreciated the help, and we'll see everybody next time there's a video. Take care.